Yeah, ladies and gentlemen, welcome to our webinar LVRSys, the solution for voltage stability problems. And to introduce myself, my name is Stefan Hoppert. I'm managing director, one of two at the Eberle company. And here I'm a speaker today because I started to join Eberle 13 years ago with this topic LVRSys. And my colleague, Thomas Schwarz, will introduce himself.
Hello, welcome also from my side. My name is Thomas Schwarz. I'm working here for Eberle since 9 years on this topic, low voltage regulation. And we are happy to introduce to you today our solution to make a stable voltage in your grid.
Just for a hint, by participating, we will record the meeting, and if you are using our chat functionality, your name might be you'll be seen on the screen. Okay, if you are agree, please take part, and of course now we have fun. Now have fun with our product presentation. So just to introduce the company briefly. So Eberle was founded in 1980, and with meanwhile more than 100 employees, and we are active in all of the voltage levels. So means from the low voltage level up to medium voltage level to the highest and high voltage levels, and we are operating internationally and in more than 65 countries. So the most of our customers are utilities and grid operators. And yeah, therefore, also this presentation was made for exactly these kind of customers. So just to go through the agenda. So at the beginning, I want to introduce the topic of electromobility, photovoltaic systems, because therefore we gain a lot of new challenges for the low voltage grid. And I will introduce you in our low voltage regulation system. It's for us, it's called as an economic alternative to line expansion. And later on in this presentation, Thomas Schwarz will explain you the functionality and gives a lot of practical application examples. So just for the beginning, for the topic, because the topic is worldwide in the news. So it's going about the global carbon emissions per year, and you see at this time of graphic, so up to 2100, the climate change will be there. The temperature worldwide is rising, and just for example, if we are going through with normal current policities, it's about global warming about 3 degrees. And if we are, if you're looking to the targets and pledges, so the temperature will rise to 2.4 degrees, and if we're really optimistic about 2 degrees, and if we want to be on the line with the Paris Climate Conference, so have a look to the green curve. So then we must reduce the carbon dioxide emissions a lot. So to halve it to the next 10 years and halve it again to the next 20 years. So if it's reachable or not, that should not be the topic today, but we want to show you what kind of trends will be there because of this situation. So we will have more and more renewable energies in the grid, and it will be there more and electrification of the mobility and also electrification of the heating sector. Especially in Europe, we made the experience that last year and this year, also because of the conflict between Russia and Ukraine, the most of the households want to be not dependent from the Russian gas, so more and more heat pumps will come up, especially in Europe. So just to go through the PV worldwide, so PV is a really strongly growing market. You see, especially the last 2 years, so the year 2022, so the graph on the left side, and the year 2023. So just the increasing, so the growth was 38% in 2022. And in this year, is it expected that the increase of photovoltaic will reach 53%. And it's a worldwide issue. And the right graphs should show you that it is a worldwide issue. Of course, in Europe, especially Germany and Spain are the leaders here, because they are more or less the biggest countries. And even in Asia Pacific, so China is absolutely on the top here. But also India is coming up really fast. And in this year, especially in India, is it expected that the installation demand will be more than 17 gigawatts this year. Also in the United States or Brazil or Mexico, the growth is really, really fast. Especially in the United States, the growing rate is more than 100% compared to the last year. So not in this kind of increasing, but it's also an upcoming situation topic. It's electric vehicle. And here the graph shows you the electric vehicle sales by region and country. And up to this point, the electric mobility is mainly driven by China at the moment. So, but it's expected that even also in Europe or in the United States, there will become a big amount of electric cars in the grid in the next years. So the rest of the world at the moment is not really there, but it's also coming up when the prices of cost of this industry and scaling market will go down. And then also it's becoming more affordable of the rest of the world that more and more electric vehicles will come into the grid. Of course, if you are compare it with the total amount of cars, so the total amount of cars worldwide, it's about 1 billion. So then you see it's just 1% of the cars is electric driven at the moment. So therefore, there's a huge potential for electrification, the mobility. Heat pumps. It's a little bit a complicated graphic, but it's a graphic shows you worldwide a situation. And I just want to make small examples. So the first green bar shows you the global heat pump increasing to the growth rate. The growth rate worldwide this year was about more than 10%. And here you see also the third bar shows you the Europe increasing. So it's about more than 40%. As I have explained to you, it's mainly driven to the Russian and Ukraine situation. But this heat pump story is also a worldwide story. So that means we have new electric loads like heat pumps and electric mobility. And of course, we have on the one and the other side, we have a lot of installations on PV, wind turbines and something. So you can read a lot of in the news, and also just for the distribution grids. Here I made just two examples with headlines that, for example, the Greece power grid is in a risk of blackout due to high renewable share and drop of demand. And also the growing demands puts electricity grid under pressure. So you can find such headlines worldwide. So these kind of stories, the stories which will continue the next years, decades or centuries, will bring to the grid more voltage fluctuations. And that means in all of the grid levels, not only in the low voltage sector, also in the medium and high voltage levels, the voltage fluctuation will increase a lot. So that brings us more and more together with our product LVRSys, because due to these expectations of the voltage fluctuations, we started with the first pilot projects 12 years ago, and we also were really surprised at this time when we saw such PQ measurements at this time. So PQ measurement like this here, you see a really unbalanced voltages and fluctuating voltages in a normal grid in Germany here especially. And at this time, the most of the utilities, they went for conventional measures. So in the distribution grid, What does it mean? So they went for expansion and reinforcement of lines and also local power stations. So that was at this time the tool to bring the voltage fluctuations and the voltage stability into a proper way. So, but what does it mean? What does it mean, especially now? So with line expansion, it's combined with really huge costs, and you have a planning and approval situation which needs a lot of time. It's absolutely intensive of personnel. You need a lot of stuff to do it, and it doesn't solve really the problem or the issue. So when we are talking about voltage stability, then line expansion and to bring up new power stations is not the most efficient and common way to handle it. So because utilities always have to ask themselves a question: how often does really a fuse blow in the distribution grid due to overload? It's a really seldom phenomenon. And therefore, of course, we propose, therefore, to take an alternative, and the alternative should be our LVRSys. So we call it here, to take it like an easy expression, we use it as a controllable distribution cabinet. So grid utilization is not a problem normally, and therefore we propose our system. So this slide should introduce you in a really briefly way of the functionality, what the system stands for and what the system is doing. And the system is there for meeting the requirements of the EN 50/160 and also of the compliance with it's a German European rule, but there are worldwide rules for voltage increase and voltage drops. Here the system is easy, this functionality is easy explained. The system brings the left unbalanced, unsymmetrical and fluctuating voltage to the right one. The right one means we control it to the reference value and bring the voltages between the limits. How can we increase the performance also in the distribution grid? So for this kind of story, I have example, because if we are facing the voltage stability and the voltage increasing issue, and then I do this small example. The white and the red or orange bar line should show you two different cables. So a 240 square millimeter cable, aluminum cable, or a 150 square millimeter aluminum cable. And to make it easy, because I know in Europe especially, the 150 square millimeter aluminum cable is an absolute standard cable. And if we are taking a look to that cable, and if we want to meet the voltage drop, the directive 4105, that the voltage drop should not be more than 3%, or the voltage increase also should not be up to the limit or more than the limit 3%, then it's and if the power plant, so the photovoltaic inverter, is about 450 meters away from the power station, that means to meet the 3%, it's just allowed for the inverter to implement or to supply the grid with 45 kilowatts. So that's the story on the left side. The same story on the right side, but improved with our system LVRSys means, just for this example with a 6% system, then we can increase the voltage by 9%. And 9% means that the same power plant, the same inverter, could be there to supply the grid with about 135, 140 kilowatts. So that means we can utilize this grid more than by a factor 3 to 4. That means taking care of the voltage with our system, you can utilize the grid by factor 3 to 4. The easiest applications, of course, from our understanding, are the PV systems. It's the easiest and most common way. Also electric mobility, capacity expansion, heat pumps. These are easy stories because PV, the voltage then is increasing, electric mobility, heat pumps, the voltage will go down, and therefore our systems are always prepared and there for highering the voltage and lowering the voltage. But we have also really interesting stories like replacing of 1000-volt connections or dismantling of local power stations, reduction of grid losses if you're more or less an expert and you know what you're doing, and high flexibility in the connection with the local power stations. But the most important point for us also is the maximum in flexibility for the future of the distribution grids. And for this kind of story, I will make easy understandable example. So because of PV and stories, heat pumps and so on, the grids are in transition. And just to give this easy example, the grids are in transition and maybe we are in the year 2023 and we have a normal origin grid without any voltage stability issues. So if we go further 2 years here, there might be, because of new photovoltaic inverters, there might be some local overvoltages. And what can utilities then do? Utilities know they are a classic alternative, so they can fix it classic, so the voltage stability, and they can also fix it with our alternative LVRSys. So in the classical way, here they used a new distribution transformer station. With the alternative, they used our system to just fix the local overvoltages. So then 2025, we fixed it both. So we fixed it alternatively, we fixed it also with the classical way. So then 2 years later on, it might be because of the situation is running further, then it could be that we have new inverters in the grid and also maybe new household because the grid expansion is there. And then we have the next story of local voltage stability issues in a different area. So, of course, the same would also happen when you have fixed it 2025 with our system. But then, in the year 2027, you have a new situation, means a new situation that not only the voltage stability is an issue, so also the utilization of the distribution transformer or the lines are an issue. And with the classic way, if the utility run only for the classic way, so here you see they have built up 2 stations in this period of 4 years. When you have done it with our alternative way with an LVRSys on the right side, you see now we had to fix it classical because utilization went out, but then you can take our system and bring it to another field application. And here the most difference is that here you miss one of the station. So here, because of the flexibility of our system, we saved a lot of the costs and not costs of this grid. So because you can take the system LVRSys to a new field application. And that means in total, the LVRSys avoid absolutely unnecessary investments in the grids. We know, especially in Germany, middle of Europe, also abroad, like in Africa, we are worldwide active. So we are worldwide present, and we know that there are a lot of different grids. And that means, so we have to, and we offer a modular system, not just modular system, what's the power size means. Of course, the power size, we build system are from 22 kVA up to 630 kVA. And also the control range is different. We offer control ranges from 6% to 10% plus minus, or even up to 24%. because in the middle of Europe, so the most common range is about ±8%, and abroad in areas where the lines are really long, distances are long, so we sell a lot of systems with ±20%. At this time, also to say, we also offer pole mount systems, even pole mount systems for single phase applications. The most common system in the center of Europe is here at the left. One, it's called from us the size one. It's a GRP based system. So our controller is based in a GRP cabinet, and the controller itself is it's a cabinet in cabinet solution. And on the right side, you see there is a connection NH disconnectors. And here you see also customers could implement and integrate completed distribution cabinet in our system. So we are that flexible that we can also integrate existing distribution cabinets to our system. For Inter systems, the size is different. The behavior is the same, but the size and the construction is a little bit different. So here we take care about the square meters, so not of the height. So we take care of the square meters. So it means the systems are not really wide, they are not really depth, but they are high from 1 meter 80 to 2 meter 20 to save square meters. Just to tell you a short story why we are convinced that we are offering the best solutions for the utilities. That it's a story because we had a lot of pilot projects running in the field, and we were very often in discussions with utilities. And we made the experience that at the beginning of the time, the utilities, they were, they wanted to test the technical principle. They wanted to test the functionality. So it really didn't matter for them what's about the size, what's about how to bring it in operation, what's about the commissioning. That was not a story at this time. They were more interested in the technical story. How did this kind of technique could solve the voltage stability issues? And then we brought more than pilot projects into the field, and we had a lot of discussions with utilities. And then the utilities more and more gave us hints to bring it in a direction of a controllable distribution cabinet. So you see the left side was a really huge cabinet, indoor cabinet. So the picture in the middle shows you the first serial projects, also 2014, where we used NH separators. And on the right side, now we're using NH disconnectors. And here we have the cabinet in cabinet design. That's a design for utilities that they really can rely on, that the controller itself is secure and is against protected rust and humidity. And it's easy for utilities then to connect to the NH separators, the incoming and the outgoing cable, and bring the system very easily into the bypass mode and also out of operation without any knowledge. And that was really important. The most of the customers said to us, this system will only be implemented and integrated in our grid when the staff who are dealing the normal low voltage distribution cabinets, when the staff are saying that's really an easy product for me. At this point now, thank you. I want to hand over to Thomas. He will explain you the practical things of the system.
Thank you, Stefan. So now we come to the point, how is it working? How can we install the system? Here on the left side, you see a real system in the field, which is not digged in. So the base is down here, it's from concrete, and you can imagine that the cables are coming from below and are connected to the NH disconnectors. Here on the right side, you see the drawing where the cable is coming, and it will be connected easily to the NH disconnectors. This can be with frame clamps or with cable lugs. It's both is possible. And then we go back to the customer from the other NH disconnector. In between, we have a bypass, which allows you that you can make maintenance or make the commissioning whenever you feel free. So the installation can be made before from guys who are not really knowing what the system is doing, but they know the installation. And afterwards you can go there and make the commissioning and starting of the system. From our experience, it's mainly in the beginning to get confidence to the system. People are asking us to help them with the first system to install it and to make the commissioning, and the other systems, they do it by themselves because it's pretty easy. It's just setting up the base, putting the transformer in the base, and then connect the cabinet and the cables. It's basically easy, and that's what was our target, to make it as easy as possible. So here we see some pictures below the transformer as it looks in the real pictures. Here we can see a cabinet which stands on the pole, so the cable are coming down from the pole and get connected to the cabinet. Other applications are just normal GRP cabinets in the field, or even pole-mounted systems. So here you can see a guy working on a pole. This is more in the southern part of Europe at the moment, and in grids where we have a lot of overhead lines installation. For the regulation principle, Stefan already showed you how it looks in the measurements. Here we can see on the blue line, it's the voltage, which goes above the tolerance band plus, and then we make a step down to come back into the regulation range where the regulation is inactive, and if the voltage goes below, it would step up, and then we are back in the regulation range. The regulation speed will be limited to a factor, we call it regulation time, and it's the area above the tolerance band or below, and it can be set in the menu. So now we come to some applications which we have in the field. Here you see one LVRSys in front. In the back side you can see photovoltaic systems. It's a large photovoltaic plant on a rural area. This is one of our main applications, that we have photovoltaic systems and which would raise the voltage too high, and we regulate it down so the connection can be done. And here is the line which is coming for this application. Here is the feed-in from the transformer, and there are 700 meters towards our LVRSys. And on the LVRSys are two PV systems. Here you can see the complete roof is full with PV, and also here. So in total, it's like 400 kV peak installed PV system, which would raise the voltage really high. And here you could see the measurement before we installed the LVRSys. So the voltage goes quite high. In Europe, we have the limit of plus 10%, which means 253 volts, which if the inverters go higher, the voltage, the inverter would stop the work. So that's the point why we come into the game, because the utilities mainly have the problem with they allow to install the PV systems, or they have no other choice that they can get connected. And when the inverter is not working anymore, the customer is complaining that it's not working, and then they have to find a solution. And here is the LVRSys one option for this example, which we have seen here, would be the calculation for the voltage. You see the orange line goes up to above 110%, which would be in maximum if it's full load. And here it would show the example that the LVRSys would regulate the voltage back into the limits, and then the voltage would rise towards the PV system a little bit. So in the end, the voltage would be regulated and the problem would be solved. For this, we had the planner of the PV system, photovoltaic system, had two options. He had on the one side the classical cable reinforcement or line reinforcement for the power of 400 kVA, and he normally uses 4 times 240 square millimeters, and the option would be to even put 2 parallel cables for 700 meters, or to make the voltage drop not that high, he should have to put 7 cables parallel. So which would be a really high cost. So at the moment, the copper price is even, or aluminum prices are even higher. So this is just an example explanation. In the end, he decided to put 2 parallel cables and install an LVRSys, which with a 400 kVA and 8%, as we have seen, here is installed and it costs around 30,000, and he would save, instead of the parallel cables, still a lot of money for this installation. Another point, as Stefan already said, heat pumps are coming more and more important because of the change in, because we have to get rid of heating via fossil fuels. More and more heat pumps get connected, and at the moment we already realize here in Germany that we get also voltage problems through the heat pumps. And heat pumps are critical because in the winter times, if it's getting cold and the heat pump is not working, then you really get a serious problem, and they will come back to the utility and you have to solve it. So here we can see the voltage on how it looks like, are the 3 phases, and the lower line are the minus 10%, which are in Europe the minimal voltage which have to be supplied. So it's 207 volts, and if the heat pump is seeing a voltage which is lower, most of them will stop working. So this is in May this year, so it was not that bad, but you even see some spikes which are going down. So in the winter times, you can imagine if you have more heat pumps connected, then you get a serious problem. And this was what happened for a customer of us. The voltage was too low and he had to solve it, because if they have no heating, they get problems in their house, things are getting frozen. So they had to solve it, and their solution was to put an emergency power unit with 250 kV for just one house, which would be far too big, but it was the only one they had. And the consumption of this emergency unit is 50 liters per hour in full load. And for this point, it was running for 170 hours almost, and cost them 4,000 euros. Just for this some hours, which was working. And the solution with our LVRSys was then that they installed an old version, which they already had in store, because they reinstalled it from somewhere else, and they could solve it. So in the end, it costs about 15,000, and then the problem is solved. And yeah, if you can imagine, it would run the whole winter with this emergency unit. It would be really costive. Another point, the e-mobility is getting also more and more. So in residential areas, if they build new houses, they mainly have the possibility to also use electrical mobiles, e-mobility. And Here is the problem: if the voltage would be too low, the charging would take long time, and also other devices can get problems while working. For example, the heat pump. If you install the heat pump and you connect your big electrical car, it could be that the heat pump stopped working, or both are not working proper. So here you can see the charging process of the voltage. Here is like 230 volts. The voltage is even already quite low, and here would you start the charging of the electric car, and here would be the end. You see the voltage drops down, and after it comes back to the normal level. This is a normal charging process which can happen if the grid is strong. You doesn't see the voltage drop that high, but the problem is if you get more and more electrical cars in the grid, this can be the normal way, that your voltage would be really low, and then you have no other way instead of the reinforcement or an voltage stabilizer like LVRSys. So here also our solution could be a reinforcement of the cables. So in this application, it was like they had to even put 700 meters underground cable, 150 square millimeters, and they calculated the cost for about 14,000. But you know, it's not always easy to dig 700 meters ground cable. So if you have the possibility to make an easier solution, you just dig one hole, you connect our cabinet in between, and yeah, the problem is solved. Then even if the cabinet would be more cost, had a higher cost, it's still the easier solution. So, and it's quite fast available, and then you can forward the reinforcement till it's really necessary. So we are now coming to the conclusion. I hope we get some questions from your side. So we wanted to show you that our system is quite easy for installation in the grid. You can connect it to different networks. It's robust, and it's made for up to 40 years of work. So we plan to combine it. Our target was to design it like you can compare it with a cable expansion or a line reinforcement. And there the utilities plan for 40 years. So all our components are made that they have more or less no lifetime problems. The heating, there is no active heating in the cabinets. So all there is no moving part inside the cabinet, which makes it really robust and long-term working. And yeah, now Stefan will make a short conclusion, and then we hope to get more questions from your side. Thank you.
Yes, thank you, Thomas. So we have seen that there are new stories coming up into the grid, especially in the low voltage grid, and therefore we prepared a system which helps utilities, especially for saving money. That's the most important point. To have a flexibility solution, a flexible solution for the low voltage grid, which saves a lot of money and also time. That's also an issue. So that means, so the last sentence here, the LVRSys equips the distribution grid of the future, and that's a really important point. So coming to the questions, we'll have a look to the questions, and we start with the question here. Our understanding of the LVRSys product is that the range can be shifted if required. In other words, the 10% a la carte configuration has a 20% range, 10 up and 10 down. And the range isn't always linked to the baseline of 0. What we are trying to understand is whether or not we can set the range to start plus 5% and end minus 15%. It depends. So the system itself, when we offer a standard system like plus minus 10%, to be with this example, plus to the question, plus minus 10%. The normal set point, the 0 point is always 0, so 0%. So then we shortage the transformers and we have the 0% situation. When you want to move the 0 point, then we have to add another transformer per phase. That means then we have to add especially a plus 5% transformer in general. Then with plus 5% transformer plus our control range means a 5% transformer plus the 10% control range means plus 15%, and plus 5% transformer minus 10% control range means minus 5%. With this another transformer, we can move the 0 point. That's right.
Okay. Next question. Do you also offer some simulation tools that incorporate presented solutions for a specific case? For example, if I want to have some preliminary analysis for using our LVRSys. So you mean the voltage drop which we showed, though we have an Excel tool which we use, but it's mainly for our partners and our sales guys, that they will help you with the calculation. So if you don't know your partner, but I think you're from Slovenia, so it would be LVRSys in Croatia, they can help you with the calculation if you have a analysis, and then they will make you a recommendation how it can works. Or they come to us and ask us if we can help them with this calculation.
So next question, what is the recommended tolerance band? It depends, but I can tell you that when the system leaves the factory, so the normal values are a plus minus according to the step size. So means if you have a system like 10%, then the step size would be plus minus 2.5%. So step size is 2.5%, and then the tolerance limits are the set value, the reference value, then plus 2.5% and minus 2.5%.
What is the expected lifetime? I already said that our expected lifetime is 40 years, so we want to compare it with a grid expansion of cables. And yeah, we use thyristors, which have more or less, like we use them, no lifetime expense. This is the main part of our system. And yeah, besides this, we hope that it will be 40 years. And that's we can also make you an example how we make the service life planned.
So just to add, we cannot prove that the system run 40 years because we do not have any systems installed for 40 years. That's clear. But the construction is made for that. And as Thomas mentioned, we have no moving parts there. Our electronic is that kind of robust that the construction is made for 40 years. And even if there are some issues, the controller itself is like a plug-and-play, a card solution. If there is any issues to the controller, you can get the material, you can get safe parts, spare parts, and you can do it by yourself, and it's easy to help the systems on running. So next question was lifetime. Hello, does your LVRSys regulate individually each voltage lines? Yes, that's a good question. It was very important for us that we do not only improve the voltage stability, we also want to improve the balance of the voltage, the three-phase voltages, and therefore each phase is individually controlled.
Okay, next question. The cost analysis you show does not show the cost of the energy loss due to the resistance of the low voltage grid, who typically bears the cost of those losses, the utility or the consumer. So in this point, there are two different ways to see it. So our system has a working point of 99.7%. So it's almost there is almost no losses, and the energy losses depends on the current. So if you have a grid where the voltage is really low, like 215 volts, and you rise it up, then the consumption, the current would be less. So if the same power is going with a higher voltage, you have less current, which makes less power losses. And the point is, you ask if who will pay the losses. It's depending. It's normally the utility paying the losses, because the customer is just paying from their point where they have the connection. They pay the amount, the power they are consuming. So if you have a higher voltage, the power losses towards the customer would be less, and then you have to pay as a utility less power losses.
What is the total correction time? It depends on the set point. So it's a parameter. So just to make an example, if the parameter is 1 volt second, so then if the voltage exceeds the limit by 1 volt, then the parameter says after 1 second, then the direction of the controller comes. So, but if you want to go to the to the fastest way, that means the controller itself could control the voltage in 25 milliseconds. That's the direction time plus controller, plus the thyristor controller time. So 25 milliseconds is the fastest way you can control the voltage.
So the next one is also for you.
The next one is for me. In marketing perspective, how much is cost of the system in terms of ROI, ERR? Thank you. It's not an easy question, because it depends of a lot. But what we are doing, we are really open, also open book calculation. So means we compare ourselves with line expansions, and we know that customers they compare us with line expansion, and the line expansion means the lifetime for a line is 40 years, and therefore we have made a cost calculation, an overall cost calculations over 40 years, with the investment costs, with power loss costs over the complete lifetime, with commissioning costs, with maintenance costs. So maintenance, we say the system is maintenance free, but of course we recommend utilities to go there every 5 years and take a look to the controller and to clean it up, to tighten the screws. And that means after 5 years you have a period of maintenance. And we made a sheet. We send also this kind of sheets, and then you see the overall cost over the 40 years lifetime. And then you can compare it to the alternative you have in mind.
So I think we have now all the questions. So then we would say thank you for your attention. And if you have further questions, feel free to contact us. Tomorrow, our colleague will send you the presentation and also a link to this webinar, that you could share it with your colleague, which maybe could not attend here. But there is one question more. Thank you for did use some PQ measurement, especially flicker. So this point is also coming often to us. Of course, we may make measurements of flickers, but this is a short period of voltage drop or flicker, and we cannot solve it with our system. So if the voltage drop would be for less than 10 milliseconds, which is a typical time for a flicker, our regulator is just doing nothing, because he cannot regulate it that fast, and that therefore he will not react on it. But in general, our system, if the voltage would be low already, and then you would come a flicker, then it would affect the devices. If you have a regulated voltage, which would be higher, it's not like 220, it would be 230, and then the flicker would come, it would not be that deep. So in this kind, our system could improve it, but it cannot solve flicker. There's another question. What about communication? For example, could be remotely read the status and other values. Yes, of course, this is possible, though there are different ways to get it. So one point would be a Modbus communication via Ethernet or the 104 protocol. And the other one would be to get just a status contact of if the system is working or not, so just on or off. And this can be connected with different possibilities to have it a mobile connection or cable. But in general, our customers, they use the communication for the beginning to get a knowledge about the system. But in the end, they say, okay, we trust the system, and we have more problems with the communication towards this cabinet, because you see there are somewhere in the rural areas where you have almost no mobile connection, or a cable connection is not possible. And then you have always the problem of communication. So they say, okay, if there is a problem again, the customer will tell us, and then we can solve it. So they use the customers in general to make the status of the system.
Okay.
So then, now I think we have all the questions. Thank you. And yeah, we're looking forward to get in contact with you.
To get in contact and get another questions. So have a nice day. Bye-bye. See you.
Bye.